Alright, so I'm going to look at a few more questions looking at momentum and Newton's laws. This time in the context of X-Men. So we've got the Juggernaut here, who according to the films or comics or whatever is impossible to stop once he reaches top speed. However, if you study physics, obviously you can work out that that's utter rubbish and he can be stopped if you apply the right force for the right amount of time. So he's currently going at 10 meters per second and has a mass of 120 kilos. So in order for him to stop, he's going to need to experience a change in momentum of 10 times 120, so 1.2 times 10 to the 3 Newton seconds. So using Newton's second law, the change in momentum is equal to the force times the time it was applied. So we can get the force by taking the momentum and dividing by the time over which the momentum changed. So 1.2 times 10 to the 3 divided by 0.1 to 1.2 times 10 to the 4 newtons of force required. The next part says, what force would be required if it was applied at 45 degrees of motion? So if we think the motion of Juggernaut is like this, and our force is now being applied at 45 degrees. So in terms of constructing our right angle triangle here, so this is the force we're applying. So what we're going to do is we're going to split it up into components like this. And we know that this side of our right angle triangle has to be equal to 1.2 times 10 to the 4 because we want to stop Juggernaut from progressing further. So F times cosine of 45 is equal to 1.2 times 10 to the 4 because you've still got to stop him. So that gives you a force when you divide both sides by cosine of 45 of 1.7 times 10 to the 4 newtons. So you have to essentially give a bigger force because some of it is not acting to change the momentum of Juggernaut in that direction, it's going to change it in the other direction. Okay, so that's the question with Juggernaut. So we've got a question about Storm. So we've got the scenario. We've got Magneto's thrown an 800-ton Golden Gate Bridge towards a building full of defenseless people. Obviously Golden Gate Bridge is full of metal, so he can throw it. And Storm uses the force from wind to stop the bridge before it reaches the crowd. So Magneto gives the bridge the initial velocity of 15. So essentially the initial momentum is 8.00 times 10 to the 5 because it's 800 tons times by 15, which is 1.2 times 10 to the 7 Newton seconds. So if she's going to stop it, she is essentially going to need to get rid of all that momentum. So the force times the time it acts has got to be equal to that. So then if we've got the force, so we essentially need to get the time, we're going to do the momentum divided by force, so 1.2 times 10 to the 7 divided by 2 meganewtons, so that's 2 times 10 to the 6. So that's going to end up being 0.6 times 10 to the 1, so it's just going to be 6.0 seconds once you calculate it. So if Storm only applies the wind for 4 seconds, calculate the velocity of the bridge. So the change in momentum, if you apply a force of 2 meganewtons for 4 seconds, is 8 times 10 to the 6 newton seconds. That's how much momentum changes. So the final momentum is going to be the initial minus the change. So it's going to be 1.2 times 10 to the 7, or like 12 times 10 to the 6, minus 8 times 10 to the 6, which is 4 times 10 to the 6 Newton seconds. So that's the momentum after the force has been applied for that period of time. And then, so if we seconds. So then the final velocity is going to be the final momentum divided by the mass. So 4 times 10 to the 6 divided by, 8 times 10 to the 5. So it's going to be 0.5 times 10 to the 1, so that's going to be 5 meters per second, which, given that it was applied for 2/3 of the time, it's lost 2/3 of the velocity. That kind of makes sense. So after the 4 seconds, the bridge strikes a building in a collision that lasts 0.5 seconds. The building is designed to survive impacts of 800 kilonewtons. Does it withstand? So we know how much momentum it has, 4 times 10 to the 6. So that's 4 times 10 to the 6. So the force is going to be the change in momentum when it strikes, so it could, in theory, lose all that momentum. So that's there. 4 times 10 to the 6. It says the collision occurs over half a second, so 0.5. So that's going to be 8.0 times 10 to the 6 newtons. So if we look, it was said that it could survive a 800 kilonewtons, so that's 8 times 10 to the 5. So the maximum it could stand was 8 times 10 to the 5 newtons. So it absolutely cannot withstand that, and you wouldn't really expect many buildings to be able to survive being hit by the Golden Gate Bridge, which is pretty monstrous. Okay, so last question. So we've got Wolverine trying to take down an enemy helicopter, and what we're going to do is use conservation momentum here. So we've got, let's create our diagram here. So we've got 100 kilogram Wolverine, we've got an 800 kilogram helicopter. So it says he's initially running at 8. Helicopter is initially stationary, rebounds at -2. So we want to essentially set it up like this. So we want to know the impulse experienced by Wolverine. So an impulse is a change in momentum. So that's going to be the mass times the change in velocity. So it's going to be -2, because it's always final minus initial, -8. So it's going to be essentially -1,000, so -1.0 times 10 to the 3 newtons seconds. That's the impulse that's acted by Wolverine. Part 2. Force is going to be the impulse divided by the time taken. So -1.0 times 10 to the 3 divided by 0.2. So it's essentially times by 5. So it's going to be -5.0 times 10 to the 3 newtons. There. By applying the Newton's third law, calculate the velocity of the helicopter. So the impulse acting on the helicopter is going to be equal and opposite to the impulse acted on by Wolverine. So it's going to be plus 1,000 newtons. So then we know that the change in momentum of the helicopter is going to be 1,000 newtons seconds. So the change in velocity is going to be 1.0 times 10 to the 3 divided by the mass, which is 800, which is going to come out as 1.25 yada yada, which is going to be 1.3 to 2 significant figures, which would be appropriate here. The final stage, verify that this result is the same as would be produced by conservation of momentum. So the initial momentum is 8 times 100, so 800 Newton seconds. The final momentum is minus 2 times 100 plus 800 V. We know those two have to be equal to each other because total momentum is conserved. So we have that 800 is equals minus 200 plus 800 V. So we know that V is going to be, take the 200 over, so 1000, divided by 800, 1.25, again, 1.3 meters per second, to two significant figures there. So we get exactly the same result using Newton's second and third laws or using conservation of momentum. So they're just different expressions of the same thing.